Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from DeepSeek AI mHC, Manifold-Constrained Hyper-Connections. Residual connections are one of the quiet heroes of deep learning. In ResNets and transformers, each layer adds a small change on top of its input, and the input itself flows forward unchanged. That simple identity path is a big reason we can train very deep models. Recently, hyperconnections pushed this idea further. Instead of a single residual stream, they expand it into multiple parallel streams and learn how to mix them. This richer topology improves performance, especially in large language models. But there's a catch. Once you start freely remixing these streams, you lose the clean identity mapping that made residual networks so stable in the first place. Hyperconnections look attractive on paper, but at scale they run into two serious issues. First, the residual mixing matrices are unconstrained. When you multiply many of them across dozens of layers, the effective mapping can blow up or shrink signals dramatically. In practice, this shows up as loss spikes and unstable gradient norms when training large models. Second, widening the residual stream isn't free at the system level. You now have to move and store n times more residual data, which increases memory access, GPU memory footprint, and pipeline communication. So HC gives you more expressive topology, but at the cost of both numerical stability and hardware efficiency. The core question in this work is, can we keep the expressive power of hyperconnections without sacrificing the stability that made residual networks so successful? We want multiple residual streams and rich learnable mixing, but we also want the effective mapping across many layers to behave like a well-conditioned identity. That means no exploding or vanishing signals in either the forward or backward pass. And because we care about real-world large language models, any solution also has to respect hardware constraints, memory bandwidth, GPU memory, and pipeline parallelism. Manifold-Constrained Hyperconnections, or mHC, tackle this by putting geometry around the residual mixing. Instead of letting the residual mixing matrix be arbitrary, mHC projects it onto a specific manifold, the set of doubly stochastic matrices, also known as the Birkhoff polytope. These matrices have non-negative entries, and every row and column sums to 1. Intuitively, they act like convex combinations of permutations of the residual streams. mHC uses the Synchron-Knopp algorithm to project the learned matrix onto this manifold at each layer. In parallel, the pre- and post-mappings that read from and write to the residual stream are constrained to be non-negative, avoiding destructive cancellations. Choosing doubly stochastic matrices is not arbitrary. It buys you several strong guarantees. Because every row and column sums to 1, applying the matrix preserves the average value across streams. That's a discrete analog of conserving signal energy. Mathematically, the spectral norm of a doubly stochastic matrix is at most 1, so it cannot expand vectors in norm. That directly combats gradient explosion. Importantly, this set is closed under multiplication. If each layer's residual matrix is doubly stochastic, the product across many layers is 2. So stability is preserved across depth. Geometrically, you can think of these matrices as convex combinations of permutations, which means they mix information across streams in a controlled, well-behaved way. Under the hood, mHC keeps the overall structure of hyperconnections. At each layer, you have an n-stream residual state. mHC flattens this into a single vector so the mapping can depend on the full context. It then uses linear projections, plus learned biases and small gating scalars to produce raw, unconstrained versions of the pre, post, and residual mappings. For the pre and post mappings, a sigmoid ensures non-negativity, with a simple scaling for the post side. For the residual mixing matrix, mHC feeds the raw matrix into the Synchron-Knopp procedure, exponentiate to make entries positive, then iteratively normalize rows and columns so they each sum to 1. After a fixed number of iterations, you get an approximate doubly stochastic matrix that is used for the actual residual update. Beyond math, there's a very practical issue: system overhead. In a standard transformer, each residual connection only needs to read and write a single c-dimensional vector per token. Hyperconnections expand this to n streams, and each of the pre, post, and residual mappings reads and writes additional data. The result is that memory access per token grows roughly with the expansion rate n. Since modern accelerators are often bottlenecked by memory bandwidth rather than raw flops, this extra I/O can noticeably slow training. On top of that, the intermediate activations for these mappings must be stored for backprop, further increasing GPU memory usage and pipeline communication. To make mHC practical at LLM scale, the authors invest heavily in low-level optimization. They fuse operations that touch the same data into single kernels. For example, RMS norm, linear projections, and gating are combined so the hidden state is loaded once, processed, and stored once. They use mixed precision to exploit fast tensor cores while keeping sensitive accumulations in higher precision for numerical safety. The Sinkhorn-Knopp iterations are implemented as a dedicated kernel that also has a custom backward pass, recomputing intermediate states on chip instead of storing them. Finally, they fuse the application of the post and residual mappings with the residual merge itself, cutting down the number of memory reads and writes per token. Even with fused kernels, the widened residual stream can blow up memory usage if you store every intermediate. mHC addresses this with selective recomputation. Instead of keeping all mHC activations, it stores only the inputs to blocks of consecutive layers and recomputes the mHC parts during the backward pass, skipping the heavy layer function. There's a simple analytic formula for the optimal block size that balances resident and transient memory, and in practice, this aligns well with pipeline stage boundaries. On top of that, the authors extend the dual-type pipeline schedule so that mHC computations, especially in MLP layers, run on high-priority streams and overlap with interstage communication. This keeps the GPUs busy and limits the extra wall clock overhead to about 6.7% for an expansion rate of 4. How does this all play out in practice? On a 27 billion parameter MoE model, hyperconnections alone lead to noticeable training instability. The loss curve shows sudden spikes, and the gradient norms fluctuate much more than in the baseline transformer. When you switch to mHC, those issues largely disappear. The training dynamics look as stable as the baseline, but with better final performance. The mHC model ends up with a lower training loss, about 0.021 below the baseline in their main run. The gradient norms stay in a tight, controlled range, which is exactly what you'd expect from a design that enforces non-expansive residual mappings. Stability is important, but the real question is, does mHC actually help on downstream tasks? The authors evaluate 27B models on 8 benchmarks, including BBH, DROP, GSM8K, Math, MMLU, HeliSwag, PQA, and TriviaQA. Hyperconnections already improve over the baseline on most of these. mHC goes a step further. It consistently outperforms the baseline and usually edges out HC as well. The gains are particularly clear on reasoning-heavy benchmarks like BBH and DROP, where mHC adds a couple of percentage points over HC. So you're not just getting a more stable training process, you're also getting better task performance. Another key test is how mHC behaves under scaling laws. The authors trained 3B, 9B, and 27B models with compute-optimal data sizes and compare mHC to the baseline. Across this range, mHC maintains a consistent loss advantage. The gap shrinks only slightly as compute increases. They also track a 3B model over a long training run on a fixed 1 trillion token corpus. The token scaling curve shows that mHC's advantage persists throughout training, not just at a particular point. Combined with internal larger-scale experiments, this suggests that the manifold-constrained design scales smoothly with both model size and data. It's helpful to visually contrast the 3 residual paradigms. Standard residual connections simply add the layer output to the input, preserving a clean identity path. Hyperconnections expand this into multiple residual streams, with learnable pre, post, and residual mappings, greatly enriching the topology but losing identity structure. Manifold-constrained hyperconnections keep the multi-stream design, yet project the residual mixing onto a stable manifold. This gives you the best of both worlds, richer connectivity with identity-like behavior across depth. The authors dig deeper into what's happening inside the residual stream. They measure how much the residual mapping amplifies signals, both in a single layer and when you multiply mappings across many layers. In hyperconnections, the composite gain can reach values around 3000, which is a clear sign of exploding behavior. With mHC, the story is very different. Single-layer gains hover around 1, as expected for nearly doubly stochastic matrices, and even the composite gains across depth stay below about 1.6. Visualizations of the learned matrices reinforce this. HC often has large unstructured gains across many entries, while mHC shows more balanced, controlled mixing. This is direct evidence that the manifold constraint is doing its job. All of these constraints and kernels might sound expensive, but the authors show that the overhead is modest. For an expansion rate of 4, mHC increases training time by about 6.7% compared to the baseline. The extra flops from the small mapping matrices are negligible. The real cost is memory traffic and communication. By aggressively fusing kernels, recomputing instead of storing, and overlapping mHC work with pipeline communication, they keep this overhead under control. Importantly, the implementation is integrated into a modern mixture of experts architecture, so the approach is directly relevant to current large language model training setups. There are, of course, limitations. This paper explores a single choice of manifold, doubly stochastic matrices for the residual mixing. While this choice is well motivated, it's not the only possibility. The Sinkhorn-Knopp algorithm also gives an approximate projection in a fixed number of iterations, so there's a trade-off between accuracy and compute. On the system side, many of the optimizations are tailored to a particular hardware and pipeline configuration, which might need adaptation elsewhere. But the broader idea is quite general. Treat residual connectivity as a geometric object and constrain it to a manifold that encodes the stability properties you want. That opens the door to exploring other manifolds and applying similar ideas beyond language models.
Stepping back, this work highlights that macro architecture, the topology of how information flows across layers, is a powerful lever in model design. Hyperconnections showed that widening and enriching the residual stream can significantly boost performance, but also that unconstrained topology can destabilize training. Manifold-constrained hyperconnections respond by putting a geometric prior on the residual mappings, restoring identity-like behavior while keeping the benefits of multi-stream connectivity. The result is a family of models that train stably at scale well with compute and data, and improve downstream performance, all with a relatively small systems overhead. It's a strong signal that thinking geometrically about residual connections could be a key ingredient in the next generation of foundation models.